Hi friends, welcome to Joey's Tech. In this video, I am going to explain to you the heap sort algorithm. Heap sort algorithm is a little complex to understand. I know that. So in this video, I am going to explain to you the algorithm in the easiest way possible by telling you in detail about a few concepts that are necessary to understand the heap sort algorithm. That is why I want you to watch every minute of this video with attention. This is the array that we are going to sort using the heap sort algorithm, and in this video not only you are going to learn how the heap sort algorithm works, but you will also learn how to construct the algorithm programmatically as well as the time complexity of the heap sort algorithm. Heap sort is a popular and efficient algorithm to understand, for which you need to know about trees and heap. Now, if you don't know about them, then don't worry. I'm going to tell you about trees, heap, and a few additional processes related to heap from scratch. Let's start then and first understand what a binary tree is. So this is a binary tree. It is nothing but a tree data structure where each node has at most two children. These two nodes of this binary tree has two children, and they are known as the left and the right child. Okay, so now you know what a binary tree is. Let's understand what a complete binary tree is. A complete binary tree is a binary tree with the following properties. All the leaf nodes must lean towards the left, and the last leaf node might not have a right sibling. So this over here you see is a complete binary tree, as all the leaf nodes are left justified. That means leaned towards the left, and you see here this leaf node doesn't have a right sibling. Alright, you now know what a complete binary tree is. You are all set to know what a heap data structure is now. So what is heap? Heap data structure is a complete binary tree with two properties. Any node in a heap data structure is always greater than its child nodes, and the root node is the largest than all the other nodes. This property is known as the max heap property. Or any node in a heap data structure is always smaller than the child nodes, and the key of the root node is the smallest than all the other nodes in the heap. This property is known as the min heap property. Alright, so you have now learned what a binary tree is, what a complete binary tree is, and what a heap data structure is. Now heap sort uses one heap operation like crazy, and that operation is Heapify. To understand the Heapify operation, first we'll have to learn to convert an array into a binary tree. Let's convert the problem array into a binary tree. So basically this element at index 0 is going to be the root element. Let's put it at the root. Now what are going to be its child nodes? So complete binary tree has an interesting property that we can use to find the children of any node. If the index of any element in the array is I, the element in the index 2 multiplied by I plus 1 will become the left child, and the element in the index 2 multiplied by I plus 2 will become the right child. So the left child of the root node, which has the index as 0, will be 2 multiplied by 0 plus 1, which is going to be the element at index 1, and the right child will be 2 multiplied by 0 plus 2, which is going to be the element at index 2. Alright, so now we have the left and the right child nodes of the root node. With the same formula, we are going to find the left and the right child nodes of this node. What's the index of 12? It's 1. So let's put 1 over here. So the left child using this formula will be the element at index 3, and the right child using this formula will be the element at index 4. Alright, so now we have got the left and the right child nodes of this node. And what will be the left and the right child nodes of this element? The index of this element is 2. So let me put 2 over here. So we'll get the index of the element of the left child using this formula as 5, and the index of the element of the right child using this formula will be 6. So the left child of this element will be 10, which is the element at index 5, and there will be no right child of this node because there is no element at index 6. Index 6 doesn't exist at all in this array. Alright, so we have created a complete binary tree from this array. We will heapify it now. And what is heapify? Heapify is the process of creating a heap data structure from a complete binary tree. We can modify this to become a max heap by creating a heapify function that runs on all the non-leaf elements of the heap. So what was the max heap property, by the way, which we just learned a while ago? Any node in a heap data structure is always greater than its child nodes, and the root node is the largest than all the other nodes. This is the max heap property. To heapify a complete binary tree, we need to start from the first index of the last non-leaf node level of the binary tree, and this index can easily be calculated using the formula n by 2 minus 1. Okay, so n in our case is 6 because there are 6 elements in the array. So the index calculated using this formula is going to come out as 2. Alright, 6 divided by 2 is 3. Minus 1 is 2. This means that we are going to first heapify this subtree over here. Okay, so we need to ensure that the root node of this subtree is bigger than the child nodes. Okay, let's learn how the heapify algorithm works. So we are going to declare a variable known as I and initialize it to 2, which we just calculated using this formula. And now we are going to declare another variable known as largest and initialize it to the value of I, which is 2. Now what's the index of the left node of this subtree? It's 5. Okay, so we check if the element at index largest is less than the element at index left. So 9 is less than 10. So now we assign 5 to the variable largest. Largest is of course the running variable. Now we swap the element at index I, which is 9, with the element at index largest, which is 10. Let's do it. So 10 will come over here and 9 will be here. Alright, the swap has happened. Now pay attention. Heapify has to be a recursive function because now it has to be applied to the subtree that starts from here, because the largest variable now contains 5. But in this case, the algorithm has hit the leaf node. So even though the recursive function will be called, nothing will happen because there is no left and right child for this node. Alright, so the heapify function has been applied on this subtree, the root node of which is represented by index 2. Now it has to be applied to this subtree, the root node of which is represented by index 1. So the value of I will now be reset to 1. The value of largest will be reset to the value of I, which is going to be 1. And what's the index of the left node of this root node? It's 3. So let me put 3 over here. Now we are going to check if the element at index largest is less than the element at index left. So 12 is not less than 5. So we don't need to do the swap over here. It's already greater than 5. So the value of the variable largest stays as 1. Now we are going to compare 12 against the right child. So the index of the right child is 4. What's the value over here? 6. Is 12 less than 6? No. So we don't need to swap 12 and 6. The root node of this subtree already is greater than the child nodes. So we don't need to swap here as well. Now one interesting thing, since no swap has happened in this subtree, hence the next call to the recursive function won't be made. We don't need to go down here. Okay. Alright, we now move one level up and the heapify function will start from this node. It's going to cover the entire tree this time. Okay. So the value of I will be reset to 0. The value of largest will also be 0. The value of left child, that means the index of left child, will be 1. So let me put 1 over here. And the index of right child will be put as 2. So the element at index largest will be compared against the element at index left. Is 1 less than 12? Yes, it is. So value of the largest variable will be set as 1. Okay. Now the element at index largest will be compared against the element at index right. So what's the element at index largest? It's 12. And what's the element at index right? It's 10. So is 12 less than 10? No. Alright. So the value of the largest variable stays as 1. My friends, I'm going into the details of the Heapify function over here. The Heapify function is going to check whether the value of I is not equal to the value of the largest variable. They are not equal. So this is a signal that a swap has to happen. Okay. So these two elements will be exchanged. All right. Let me put 12 over here and 1 over here. Now a recursive Heapify function call will have to be made for this subtree because the value of the root node has changed. 1 needs to be put at its correct place. So in this Heapify function call, I will be reset to 1. The value of largest will be initialized to I, so it will be 1 again. The index of the left child will be 3. All right. And the index of the right child will be 4. Right. Now, the element at index largest, which is 1, will be compared against the element at index left, which is 5. Is 1 less than 5? Yes, it is. So the value of the largest variable will now be set to 3. Okay. Now, again, the element at index largest, which is 5, will be compared against the element at index right, which is 6. So is 5 less than 6? Yes, it is. So the value of the variable largest will now be changed to 4. Okay. Now the Heapify function is going to check whether the value of I is not equal to the value of largest, and they are not. So a swap needs to happen. So the element at index 1 will be replaced with the element at index 4. So a swap will happen between these two nodes. So 6 will be placed over here and 1 will be placed over here. Okay. All right. We have heapified the entire binary tree. That means it has been made into a max heap now. Now let's quickly write the algorithm for the Heapify function. This is the soul of the heap sort algorithm, so we better write it now as it is fresh in our mind. First, we are going to create a sort function that's going to accept an array as the parameter. So I'm going to write public void sort, and it's going to accept an array as the parameter. All right. Now within the body of the sort function, we'll declare a variable n and initialize it to the length of the array. So it will be equals to arr.length. Okay. We are now going to write a for loop that is going to run from n by 2 minus 1 to 0. We just went through the iterations, right? So it will be for int I equals to n by 2 minus 1, then I greater than equals to 0, I decrement operator. Okay. Within the for loop, we are going to make a call to the Heapify function. The parameters will be array length, and the value of I. So let's make a call to the Heapify function. It will be Heapify. We are going to pass the array, then the length of the array, which is represented by n, and I. Let's create the Heapify function now. It will have 3 parameters as we saw in the function call. So let's first create it. It will be public static void Heapify. It's going to accept an array as the parameter. Then it's going to accept the array length and the value of the variable I. All right. First, we are going to declare a variable largest and initialize it to I. Now we will have to calculate the index of the left and the right child nodes. So how do we do that? We have the formula. We saw the formula over here, right? So let's declare a variable left, and the index of which will be calculated as 2 multiplied by I plus 1. And let me declare a variable right, and it will be calculated using the formula 2 multiplied by I plus 2. All right. We'll now write the code to compare the left child with the element at the index largest, which in the first Heapify function call will be the root node. That means we are going to write if array element at index left is greater than the array element at index largest. If it is, then we are going to assign the variable largest the value of variable left. Now we'll write the code to compare the right child with the element at index largest. That means we are going to write if array element at index right is greater than the array element at index largest. If so, then largest will be assigned the value of variable right. All right. Now if the value of the largest variable contains any index other than the index I, that means if the left child or the right child is found greater than the root node, then we'll have to swap them. We'll have to make the swap. So it will be if largest not equals to I, then we'll write the code to swap the element at index largest with the element at index I. So it will be int temp equals to array element at index largest, then element at index largest will be replaced by the array element at index I, and finally we are going to put the value stored in the variable temp at index I. All right. Okay, so this will do the trick, but as I told you, you will have to again recursively call Heapify function to push the element down. So we'll write the code for that. It will be Heapify. The first parameter will be array again. The second parameter will be the length of the array, very much necessary. And the third parameter this time will be the value of the variable largest. Okay, because now the element that started at the root has moved to the element at index largest. So it will be the largest variable as the third parameter. The recursive function call will only be made if the swap happens. Therefore, it will be within the if block only. Now wait a minute. In the first case that you see on the left, when the recursive Heapify call will be made, then it will find no left and right child nodes for this element, and therefore the function must be equipped to stop the comparison, otherwise the algorithm will throw a runtime error. So when the largest variable would contain 5, the left child will be calculated as 11 and the right child will be calculated as 12. How do we stop this comparison from happening? So we write one more condition over here before this condition, separated by the AND operator. And what that condition will be, it will simply check if the value of the left variable is less than n. That means the length of the array. And a similar condition we are going to write over here, which is going to check if the value of the right variable is less than n. This will do the trick. All right. Since 11 is greater than 6, hence this condition will fail. And since 12 is also greater than 6, hence this condition will fail too, and the comparison won't happen. Finally, we have written the Heapify function in Java. I must say 70% of the heap sort algorithm is covered by the Heapify function. Let's proceed further and complete our understanding of the heap sort algorithm as well as this Java program implementing the heap sort algorithm. Let's proceed further and complete it. Now, since we have applied the Heapify function on the complete binary tree and converted it into a max heap, we have the largest item at the root node and our array now looks like this. It has transformed. The next step will be to remove the largest element which is at the root node. How we are going to remove it? We are going to pick it up and place it at the nth position of the array, or in other words, make it as the last item of the heap. Of course, the element currently at the nth position or the end of the heap will take its place. So let's do the swap. It will be 9 here and 12 over here. Okay, let's do the swap here as well. It will be 9 and 12. Now the largest element which is at the end of the array, or in other words, which has become the last element of the heap, will be cut off. And the size of the heap will be reduced by 1. Now, the root node doesn't have the largest element anymore. So we'll have to heapify the root element again. So the same heapify algorithm will be applied. Let's apply the heapify algorithm again on this. So if I quickly heapify the root element, then this 9 is going to come over here and this 10 will be over here, like this. So there you go. We have the largest element at the root node again. This has become a max heap. Alright, no other change is required. Let me do the replacement here in the array as well. So 10 will be placed here and 9 will be placed here. Now we need to place the element, the largest element at the root node at the end of the heap. So what's the end of the heap? It's this element over here, because 12 has been cut off. The array in question has been reduced by 1. The size of the heap has reduced by 1. So now the nth position of the array is this. So 10 will be placed over here and 1 will come over here. Let's do the swap. So it will be 1 here and 10 over here, and let me do the replacement in array as well. 1 over here and 10 over here. Okay. Now what's the next step? We'll cut this element off as well, and the heap size has reduced again by 1. Now the array under consideration is this. Okay. And you can see the sorting is happening. Alright, you can see that the root node again doesn't have the largest element. So we'll have to heapify the root node again. So we get the largest element at the root. If I quickly heapify it, then this one is going to come over here and this 9 will come over here. Let's do the replacement, and I'm going to do the corresponding replacement here as well. I'm going to place 9 over here and 1 over here. Now we'll place 9 at the end of the heap. What's the end of the heap now? This is the end of the heap. These two are cut off because this is the array under consideration. So 9 will be placed at the nth position, which is this index 3. So let's do the replacement. I'm going to place 5 over here and 9 over here. And I'm going to do the corresponding exchange here as well. Alright. Now what's the next step? This particular element will be cut off, and there you go. The size of the heap now has reduced by 1 again, and it's limited to 3 elements only. Check here. The array under consideration now has 3 elements, and we are going to repeat the same process because we don't have the largest element at the root anymore once again. Now we'll need to heapify the root node again. The tree contains only 3 elements. Let me quickly heapify the root node, as a result of which 6 will be placed over here and 5 will be placed over here. Let me do the exchange over here as well. 6 will be placed over here in the array and 5 will be placed over here. Now we see the largest element is at the root. Now the next step will be to remove this element, the root element 6, and place it at the end of the heap. This is going to be the end of the heap, and then we put this one which is at the end of the heap at the root node. You see, this is the array under consideration. The nth position is at index 2. That is why we are considering this element to be the end of the heap. So let's do the exchange. So 1 will be placed over here and 6 will be placed over here. Let me do the corresponding exchange here as well in this array. Now, this element will be cut off now. So let's cut it off. Alright, the size of the heap has reduced by 1 again, and it is now limited to 2 elements. We'll have to again heapify the root node because we don't have the largest element at the root node. You see over here the array has 2 elements, and you see the sorting is happening. Okay, so let's heapify the root node quickly. 5 will be placed over here and 1 will be placed over here. Let me do the exchange over here as well in the array. Alright. Now the next step will be to remove the root element and place it at the end of the heap. This is the only element which also represents the end of the heap. Over here there are 2 elements only in the array under consideration. So 1 is the nth position now. So 5 will be placed over here. So let me do the exchange. So 5 will be placed over here and 1 will be placed over here. Let me do the exchange here as well. Alright, and now this node will be cut off from the heap as well. Alright, now we have only 1 element remaining in the heap, which is at index 0, which also happens to be the smallest element. So here is where the heap sort algorithm ends, and we can say that the array is sorted. So let me tell you the steps of heap sort algorithm in short again. We first build a heap from the array. We then place the largest element at the end of the heap and put the element at the end of the heap at the root. We cut off that largest element by reducing the heap size by 1, and then we heapify the root element again. This process is repeated until all the items of the array are sorted. Now let's code the remaining part of the heap sort algorithm. So we again go into the sort function. Now after this code gets executed, we'll get the complete binary tree / array turned into a max heap. So now what we are going to do, we'll run a for loop that is going to run from n-1. That means the last element to the first element of the array. That means the element at index 1. So the loop is going to run in reverse order. So it will be int I. The loop is going to start from n-1. It's going to run till the element at index 1. So it has to be greater than 0. And then it will be running in reverse order. So it will be decrement operator. Okay. Once we get the max heap, what we do? We place the root element at the end of the heap. So we write the code for that. So it will be int a temp variable. We declare a temp variable and we place the value at index 0 inside it. Okay, index 0 is going to contain the root element. Now we are going to place the element at index I at index 0. That means we are placing the last element of the heap at the root, and finally we are going to place the value of temp at index I. All right. This code is pretty much self-explanatory. Now we cut off the last element of the heap or the last element of the array, because here we have the largest element stored, and we now heapify the root node. So we make the recursive heapify function call now. We pass the array and the size that we are going to pass will be I. Now I in the first recursive function call contains n-1. N is 6, so n-1 will be 5. So the array size is reduced by 1, right? And the third parameter we are going to pass will be 0. All right. We will be only heapifying the root element. That is why we are going to pass 0 as the third parameter. Okay. So our Java program implementing the heap sort algorithm is almost complete now. Let me quickly write the main function and the code to print the array, and then we are going to run it and check if the array gets sorted or not. Alright, I have quickly written the main function and the code to print the sorted array. Let's run this program implementing the heap sort algorithm and check whether it sorts the array or not. And there you go. The array is sorted. This was the problem array, and this is the sorted array. That means the program implementing the heap sort algorithm works. The time complexity of the heap sort algorithm is big O n log n in the worst and the average cases. With this, we have come to the end of this video. I hope you enjoyed learning the heap sort algorithm from Joey's Tech. I have created videos on other important sorting algorithms as well, and you must watch those videos in order to learn those sorting algorithms properly. I will see you in the next video of Joey's Tech. Till then, goodbye and take very good care of yourself.